Okay, so the next section is the trapezoid rule. And so we learned LRAM, RRAM, MRAM, and then the trapezoid rule. So that'll be the fourth strategy, and there won't be another one. So it's called the trapezoidal rule, and it's based on creating trapezoids instead of rectangles. And so you might think, well, why would we do that? Well, let's think about curved regions and let's look at this picture. So we saw that the rectangles can be an overestimate, an underestimate, a combination of both. But if we look at trapezoids, notice the base is going to be on the x-axis and the height, since they're the parallel lines, are going to be the y values of the function. And then when we go to draw them in on a function, there's less of a gap. And so that's why some people think this is superior, but it's not for us to judge. You will be told which method to utilize, okay? So the area of a trapezoid, just as a review, is your base, which I call my height over 2. I use h over 2 base plus base, but they're using your base since that's on the x-axis, and then your height because those are the y values. So f of x1 and then f of x sub 2, all right? So this kind of shows the notation that we can utilize. Notice since my base is going to be, they're all uniform widths, we can factor that out and then use our function values. So we can do the same setup that we did with either the notation or with the specific values, okay? So just be flexible. The trapezoid, I said this from the midpoint. The trapezoid is the average of the left and the right Riemann sums, okay? Now, be careful. The height of the trapezoid is not equal. You cannot use the formula, okay? And so what you would have to do is you would have to calculate each trapezoid area separately. Now, that typically will only show up when you're given a table of values, but that's the trap. We will practice this. If you're given a function, then you are going to have uniform widths. So there's no reason to not use this shortcut formula, all right? You're welcome to do each trapezoid individually no matter what, but there's really no reason. So I use the same function that we had yesterday. So we're going from, oops, I forgot to add in the directions. It was from 0 to 1. And so I know this is high, and we're going to go out 9 minus 4x squared, and we're going to use our trapezoids. So 0.25, 0.5. I like to have a picture or at least a number line. If you don't need the picture, that's fine, but this is the idea. This is a little sliver. I'm exaggerating it because it really is tiny. It's not the exact area. We still need that integral value if we want to use that. All right, so for the trapezoid, we still have our, I'm just going to call it base over 2, and then we need all of our heights. So notice, and I'll show you I'm going to bring that formula back up, but height plus height. We've got, this would be used for my first trapezoid. I use 0, f of 0 plus f of 0.25, okay? And then my next trapezoid, I'm going to use, this is one of my base, and this is one of my base. So I get f of 0.25 plus f of 0.5. Then on my third one, I've got this base and this base, or height. And then on my fourth one, we got that base and this base. Okay. So what happens is we actually end up with, we've got 2 of those, 2 of those, 2 of those, and then single endpoints, okay? So if we look up here, and I didn't make a big deal of it, if we look at the formula, I wanted to prove it to you first. Notice it's single on the edge, double, 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 and then single on the outside, okay? And so that's how the trapezoid formula or trapezoid rule is really expedited instead of doing them all individually. So you just have to remember to double all the inside heights and just single the edges, if that makes sense, okay? So my height is still going to be, and I'll prove it up here. We've got b minus a, so 1 minus 0 over 1, 2, 3, 4. Okay, so that's the height of the trapezoid. Now, in the area formula, though, it is also being multiplied by a half. So that's the part that gets forgotten. So it really is 1/2 and then b minus a over n for the height of the trapezoid, and then your single edges, double all the ones in the middle, and then single the end. Okay, so there's a lot that gets forgotten, to be honest. It's just more memorizing. But I like to kind of show you what everything is. So notice up here, they do say b over 2. B is really each of those widths if you don't want to figure it out. So we know that each of those on mine is 0.25. So it's still half of 0.25. So keep that in mind. If you want to memorize a formula, I would memorize that part just so you're clear and you're not just doing b minus a over n. Okay, so I get 1/2, and then b minus a over n is 1/4. If I substitute 0, let's go ahead and plug that back in. And I should have saved my answers from yesterday, but that's okay. F of 0 is 9. 2 times, if I plug in 1/4, so I'll do it right here. So 9 minus 4 times 1/4 squared is 9 minus 4 times 1/16, which is 9 minus 1 over 4th, which is 8 3/4. And I always like to write it as a fraction improper, so 32 35/4. Double when I plug in a half. So 8. And you can see, for time's sake, they might just have you do the setup on this trapezoid formula because it is pretty time consuming. So 3/4. I need more room. Let's do it up here. So 9 minus 4 times 3/4 squared. 9 minus 4 times 9/16, which is 9 minus reduced by 4. 9/4, so 36 over 4 is 27/4. And then f of 1. So if I substitute 1, we get 5. And so then it's just a matter of time to clean up. Most of this would be by hand, not necessarily on the AP exam because it's a time test. And you can see how long this takes. 9 plus 5, I'm just going to add what I can. So 14, reduce that. Oops, I forgot that 16. So let's go ahead and amend that. So I get 9 plus 16 plus 5, 21, 30. And then half, so it's 27 halves, which is 1/8 times 35 plus 27 is 12, 62 over 2, which is 31. So 1/8 times 61, which is 61/8. Okay, that would be my trapezoid approximation. So you can kind of see the notation, working it out all by hand. It's really a choice. Let's look at example 2. We'll do more of these in section 7.3, but they're going to give us an application. And notice this is the rate of pollutants escaped. So remember, that really is like a derivative. Time is my x values in month, and they give us some values. At a plastic plant, blah, blah, blah. Use trapezoids to approximate the total number of pounds. So remember, what we're really trying to do is when we integrate over a year, so from 0 to 12 months of our function, we'll just put f of x. Well, that's the derivative. So that's the rate of pollutants. So when we integrate, we're actually finding the original function, which is the number of pollutants. Okay, and I always like to say total. Whenever I integrate, I always put total because you're accumulating all of those rates, all right? So if we want to use trapezoids, the first thing we need to notice is, can we use our shortcut, or do we have to do all of this by hand? And the way you decide is you look at my intervals. If my widths, which would be the height of the trapezoid, are all the same, then you can just go ahead and use that shortcut. So I know that's 1 apart, that's 2 apart, I already can't. So the only thing is you're going to have to do this using all of these trapezoids individually, okay? Now, there are shorter ways to do it without a picture, but to explain it to you, I'm going to go ahead and just get the picture. All right, so I'm going to start, and I'm going to only draw it as I go. Okay, so there's 1 trapezoid, 2 trapezoids, 3, 4, 5, 6, 7. Okay, and 7 is a lot. So if I wanted you to do this by hand on an AP test, they would probably give you 3 or 4, just so you know. So we're going to put equals. So we get h over 2 base plus base. And I really am going to do this, what did I say? 1, 2, 3, 4, 5, 6, 7. 7 times. Now, if these were equal intervals, we could go ahead and just use that formula that we did on the last example. One, 2, 3, 4, 5, 6, and I need 1 more. Okay. So the height of the first, we've got 0 is at 525 and 1 is at 700. So when we go to draw our trapezoid, remember, this is my height and this is my base and base. So we get 1 and then 525 plus 700. So you could probably do this without a picture. That's fine. And then my next one I've got right here. So 3 is at 800. So my height is 2. Base at 700 plus that. And because my heights of each trapezoid are different, I can't just double that 700 anymore. Does that make sense? So you can kind of see, like, if these were all the same intervals, then I could just do single 525, double, 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 single. All right. But that's the trap with the tables and the trapezoid rule. Okay. And tables and Riemann sums. So you have to go based on the information that's given. All right. So they might not always be equal. My third one. So let's try this without. So we did that one. We did that one. So that height would be 1. And then we got base and base. And you can see where this is going. So just to jump ahead, you can go ahead and look at the student practice and try those, or continue. I'm going to finish this problem. It's just really time consuming. So I'm going to draw it because sometimes I lose track. So 1, 2, 3, 1, 2, 3. So then I'm going from 4 to 6. All right, so my height is 2. And then 1050 plus 1350. And then my next height, so that one's done. My next height goes to 7. So 1. So 1350 plus 1500 plus my next height goes to 9. So that's 2. 1500 plus 2000. And these aren't terrible to do by hand. And then my last one, my height is 3. And then 2000 plus 2800. Okay. So this would be a trapezoidal approximation. And same thing. Trapezoids can be an overestimate or an underestimate, just so you know. So I get, what's that, 1225 and half of that, which is 612.5. I get 1 times 1500. I get half of 1850, which is 925. 1 times 1400. I get half of 1850, which is 925. I get 1 times 3500. And then I get 1.5 times 4800. So 4800 plus another 2400 is 7200. Okay, big math. So let's start adding some together. So I get, that's 5,000, 12,200, 1850, 1400, and then 612.5. I'm literally just adding the old-fashioned way. 2, this is where I totally make errors, but 10, 10, so 20, 2, 4, 5, 6, and 1. Okay, so I end up with 16,062.5. But remember, that was a total of pollutants, okay, over a year. So it'll be 16,000 pollutants, pollutants in 12 months. Okay, I always like to put total if I've done an integration. All right, so that's the idea. Okay, so some of these I want you to approximate, and notice I review with you right and midpoint rectangles. Compare, which would be the smallest and largest. I would get a picture. You do need to know what e to the x looks like. Tell you trapezoidal partitions, and they're telling you which ones to use. You do get to use a calculator. And then same thing from 0 to 1. You don't need to use individual trapezoids. You can use a trapezoid formula. I'm giving you an answer check, so just make sure your work matches up. Okay, so try those 4 and see how you do.